Now for the second question, it's a fairly simple question this as well. We have a couple of parts and we have to do integration. Mostly in Calculus 2 course, you'll have to do integration technique. Some people only in the first Calculus course would do integration technique. Wherever you do integration, you'll have integration techniques. You know the famous one, the algebraic ones, the basic formulas. And then there's this. This is the partial fraction one. Okay. The first one seems like a partial fraction. So a basic and general piece of advice, if you want to get better at calculus, just do a lot of it. A lot of algebra. If you know a lot of algebra, you can get away with a lot of stuff. So you see this, the important point of math is to recognize patterns. So if you see the denominator, you can see that it's factorable. You can in fact factorize it x plus 2, and I think it's x plus 1, right? So this is the factorization. You can do midterm breaking and then come up with this factorization. Now this is a simple factorization that you can do, but now you can see that we can use a technique which is called the partial fraction technique. In the partial fraction technique, you have an algebraic fraction. The arguments in the denominator need to be linear factors. They can be quadratic factors, but they would have a separate formula. So you can just Google partial fraction or formulas, and there would be a table for different sorts of scenarios. For instance, if this denominator was a square, there would have been a different sort of a factorization technique we would have used, partial fraction technique we would use. But these are both linear, so we'd just use a linear term or like a constant term above, a divided by x plus 2 plus b divided by x plus 1. The mathematical assumption is that these two can cross multiply and get you this. Now, of course, if you can break this into this, the big idea is that taking the integral would mean taking the integral of this whole thing. And taking the integral of this whole thing would then mean taking the integral of the individual things, because integrals are additive. Now, once you can get the additive parts of the integral, these two parts, which means solving for a and b, once you get these a and b, which are only constants, but you need to still figure out the exact values. Once you get that, this sort of an integral of 1 over x or some linear expression like x plus 2 is natural log. So you can simply solve this in that fashion. So that is why partial fractions are really important tools to be used. So let's first go back and try and figuring out the partial fractions. Now this is a simple algebraic practice. You multiply the denominator on both sides. What happens now is you need to compare coefficients on both sides. First, you'll expand this side. This would become a plus bx. I'm doing the expansion quite readily. And the other term is a plus 2b, if you don't mind. Okay? You can just rearrange this into this based on the coefficient of the powers of x. Now you see at the 0th power of x, at the 0th power of x, which is a constant term, you have 1 over here. So what I was saying was you have the constant term here should equate with the constant term here. So a plus 2b equals 1, and the term having x here is 0. So a plus b equals 0. Now you can subtract these, let's say, and this would become 2b minus b. A minus a is 0, 2b minus b is b, and 1 minus 0 is 1. So b equals 1, and also a plus b was equal to 0, so b equals minus a. This implies that a equals minus 1. Okay, so you can just work that out, and you can just plug in those values here. 1x plus 2, minus 1x plus 2, 1x plus 1. Okay, now you can just simply take the integral. That's it. So you take the integral. Now the minus sign would come outside, The integral is simply of 1 over x plus 2, and here the integral is 1 over x plus 1. I'm skipping the dx just for notation, but you should always have dx over here. Okay, now you need to make a simple substitution, but it wouldn't matter because it's a linear substitution, so it wouldn't do much. Okay, now you can simply write this as minus, this is the natural log function, natural log absolute value x plus 2 plus natural log absolute value x plus 1. Okay, so once you've done that, you need to plug in the values, which is 1 to 0 and 1 to 0. So you need to plug in the values. That is a point where a lot of people make mistakes. Let's just go through that very simply. So natural log, when you plug in 1, it's 1 plus 2, that is 3, minus another minus natural log x plus 0 plus 2 is 2. Okay, and then when you have 2 here, you should have plus natural log 1 plus 1 2 minus natural log 0 plus 1 1. Okay, so this would be plus plus, so it would be something like minus natural log 3 plus 2 times natural log 2, because there are 2 of these, minus natural log of 1. What is the natural log 1? Is it e? Okay, so this can become squared, so it's 4 natural log of 4, and the subtraction term is natural log of 3 minus natural log of 1. The natural log of 1 should be 0, because 0 is the number you get when you raise anything. Sorry, 1 is the number you get when you raise anything by the power 0. So natural log of 4 minus it's going to be natural log 4 by 3. So that's going to be our answer. And for the second part, what we can do is another technique. This technique is called by parts. You do an integral by parts. So it simply goes something like this. If you have two functions u, v, and assume that u is a function of x and v is also a function of x, I'm just implying that, and these are both functions of x. If you take the integral of this and they're in a multiplication, this is not a composition of functions, this is a simple multiplication. Now what you're going to do is you're just going to put u like this, and then you're going to integrate dx minus a whole integral. You're going to take the derivative of u, you're going to take this part again, and then integrate the whole thing again. This is a nice sort of distribution, or sort of tells you how you can expand the multiplication if there's an integral out there. And in a lot of cases like this one, this would really simply solve itself. Let's see. So let's assume natural log of x is the first function. There's a general rule of thumb. It's something like this: inverse, logarithmic, algebraic, trigonometric, and exponential. Exponential is always in the last. So the sequence of u and v, which function has to be u, which has to be v, there's a lot of nuances to that, but this is sort of a general good rule you can use. So in this rule, the type of function that comes prior should be u, and the one that comes later should be v. So in this case, x square is an algebraic function, so we'll give it the v spot, where ln x is a logarithmic function, and we'll give it the first spot. And let's see how that helps us out and why the alternative is not good. So we can put it something like x square ln x. Just let's put it in the right order so that we remember that. Ln x and x square dx. First function as it is, integrate the second one, minus integral. Derivative of ln x is 1 over x, and then there's the integral of x square dx again, and then the whole integration of that. Ln x and x square becomes x cubed by 3 by the simple power rule, again there would be 1 over x here, and this would be x cubed by 3. This would become square. Okay, so you see, this actually worked out well for us in this scenario, right? So that is a good thing. It could have worked honestly in the other way. I think, let's think, x squared, and it becomes x cubed, and then there's another 3, so there's a 9 below. Okay, so that is that. This question is then solved.